Wide bandgap semiconductors, silicon carbide and gallium nitride, are used in many different types of power applications, including renewable energy, aerospace, transportation, automotive, industrial motor and drives, and telecommunications. Silicon carbide is well adapted to higher voltages and power, while gallium nitride works well for lower voltages and power, but generally offers improved efficiency at higher switching frequencies. Both find their use, and the choice is depending on the application's requirements. In some applications, you'll find both. However, for both technologies, there's one general trend to be seen. The world's quest for sustainability and power efficiency drives the demand for smaller size, lighter weight, and ever-increasing switching speeds to support the reduced switching losses. During the development, evaluation, and finally implementation of these wide bandgap semiconductors, at some point, the performance and efficiency has to be validated. And typically, for this task, a precision power analyzer is used. But which key specifications are of significance when selecting the measurement instrument of choice? To answer this question, I will consult an expert who knows all about this topic. Michael Rietveld, you are a precision maker and the product manager for power measurement here at Yokogawa Test and Measurement. Can you tell us which are the key considerations when selecting a power analyzer for this task?
Yes, thank you, Calvin. As you mentioned, wide bandgap semiconductors are applied in a wide range of applications and they become more and more efficient. As variable frequencies offered by these technologies go up in frequency, their efficiency measurement becomes more challenging. When selecting a precision power analyzer, such as this WT5000, you should always consider first the required accuracy. Second, is accredited calibration required? And third, which is the most overlooked one, what is the bandwidth required for your application? Let me explain this to you in a few slides.
I would like to discuss this on the hand of an inverter driving a motor. The picture illustrates a typical industrial layout where three-phase input from the grid is converted to DC, which is fed into the inverter to drive the motor with pulse width modulated signals to control the torque output of the motor. Thinking this picture reverse will look like a generator and is especially true for windmills. Replacing the converter section with a battery package represents an electrical vehicle layout, but also more industrial inverters are fed directly from a DC net. First of all, it is important to understand the signals that are generated or influenced by an inverter. The top yellow and green waveforms are the DC link voltage and current. As can be seen, both show reflection caused by the switching in the inverter. The purple and blue waveforms are the voltage and current waveforms from one phase of the output of the inverter. Where the purple waveform is pulse width modulated voltage, which is used to control the torque of the motor. The next slides will explain where to pay attention to when measuring these signals. The highest frequency component that can be measured by an instrument is limited due to its bandwidth. The bandwidth of a measurement instrument is normally indicated by its -3 dB point. In other words, the frequency of which the amplitude is attenuated by 3 dB or 30%. The output voltage, which can be seen in the purple waveform of the inverter, is pulse width modulated. The bandwidth required to measure a pulse signal depends on the duty cycle. Therefore, as rule of thumb, it's easier to consider a square wave. A square wave exists out of an infinite number of higher frequency components. Therefore, a bandwidth of a measurement instrument will cause an error in the measurement. The more frequency components are measured, thus the wider the bandwidth, the smaller this error. To capture the amplitude of a square wave correctly up to 99.95%, one will need to have a frequency response of at least 400 times the switching frequency. So, to measure the output voltage of the inverter, the measurement instrument needs to have at least a bandwidth of more than 400 times the switching frequency. So if the switching frequency, which nowadays can be seen for high power applications of around 20 kHz, a bandwidth of 8 MHz is required. As we can see that switching frequencies increasing in the future, higher bandwidth requirements will be there. To measure power, a smaller bandwidth is required than measuring a pulse width modulated or square voltage waveform. The bandwidth required to measure power is determined by the least distorted signal. So for the input of an AC-DC converter, as can be seen in the picture, is determined by the current. The yellow waveform is the grid voltage and the green waveform is the switching current. In the harmonic bar graph window, we can see that there are some harmonic distortion in the voltage, but there are much more harmonic components in the current. However, when there is no voltage and there is current, there cannot be power. We also see that at some harmonic orders there is voltage and current but no power. In this case, there's a 90 degrees phase shift between these signals. However, these still should be evaluated. So the required bandwidth for power measurement is equal to the least distorted signal of the applied voltage and current. Now if we take a look at the output current of the inverter, we can see that the current shape is more triangular. This has two causes. The first one is the air gap flux of the motor, which creates zero sequence harmonics, which produce a stationary field, negative sequence harmonics, which result in a counter-rotating field, which results in reduced torque, and positive sequence components, producing a forward-rotating field that adds to the torque. This is creating the large triangular waveform shape of the current. If we zoom in on the waveforms, we can see in purple the pulse width modulated voltage with steep flanks, and in blue the current waveform. And here we can see clearly the reflection of the pulse width modulated voltage on the current signal. At each edge we can see a triangular waveform shape in the current, as it cannot respond fast enough to follow the square wave of the voltage. So to determine the required bandwidth to measure power and efficiency of an inverter, we should consider the characteristics of a triangular waveform. In other words, the question is how many harmonic orders should be included when considering a triangular waveform shape. In this table and graph, you can see how much of the total amplitude is measured when a certain number of harmonic orders are included in the measurement. And in the last column, thus the error caused by bandwidth limitation when measuring a triangular waveform. Therefore, the required frequency response to include all signal components is 25 times, or 25 harmonics, multiplied by the switching frequency, which in our example was 20 kHz. So in this case, a frequency response of 500 kHz is required. To limit the error caused by bandwidth limitation to the same degree as the accuracy of a power analyzer, a frequency response of at least 7 times the switching frequency is required. This of course is depending on the required accuracy. So, to conclude this, to measure electrical power and efficiency precisely, a frequency response of at least 7 times the switching frequency is required to limit the error caused by bandwidth limitation to be in line with the measurement uncertainty. To include the complete signal, a frequency response of 25 times the switching frequency is required. In this presentation, examples of a switching frequency of 20 kHz have been given. But obviously, this is already higher for low power applications and is increasing for high power applications. To meet future power measurement demands, a WT5000 precision power analyzer has a bandwidth of 10 MHz for voltage and 5 MHz for current. When even higher bandwidth is required, we can offer other solutions, such as our unique PX8000 power scope. When measuring power, there are more things to consider. To perform an accurate measurement, let me give you another point you should consider. In digital power meters, the electrical power is calculated as 1 divided by period time t. multiplied by the integration of instantaneous voltage multiplied by instantaneous current over an integer number of periods. Therefore, it is very important for a power analyzer to find period time t correctly. When the calculation is not done over a complete number of periods, large errors can occur. The waveform in this picture shows a signal of 100 volt RMS, which is true as can be seen when calculated over exactly 2 periods. When any other random calculation period is used, such as 1 1/8 period or 1 1/3 of a period, an error will occur which can be larger than 3%. The most difficult task for the power meter is to find the period time t correctly to ensure an integer number of periods are used to perform all calculation. And especially with higher noise levels of wide bandgap semiconductors, this task becomes more challenging. For Yokogawa, it's our expertise and we perform this measurement since introducing our first digital power analyzer in 1974. Also, our latest power analyzer has a new second calculation technique to eliminate this error. For measurement on wide bandgap semiconductors, we offer a range of power measurement products led by our WT5000 precision power analyzer. Packing the very best in isolation, noise immunity, current sensing and filtering in a modular architecture, the WT5000 is an extensible measurement platform that unlocks precision power analysis for development of energy efficient systems.
Thank you, Michael. If you'd like to know more about power measurements related to wide bandgap semiconductors, the WT5000 Precision Power Analyzer, or when you have an application-specific question, please do not hesitate to contact us. We are here to support.